Okay, so in this video, I'm going to review doing derivatives of polar equations. And, for polar equations, what we have to realize is that we want to find slope, which is dy dx, but our equations don't have x's or y's, right? It's r's and thetas. So we have to rely on some things we did in honors pre-calc. And one of them is converting converting from polar to rectangular and vice versa. And that's x equals r cosine of theta and y equals r sine of theta. And it's actually pretty easy to see just in any right triangle why that's true. If you have your your unit circle and you just have some arbitrary point x comma y. It's kind of a weird circle. That's all right. And if you have any arbitrary point x comma y on that unit circle, so x comma y. So there's a radius here that's a right angle, and that's theta. And so that means this side's x and this side's y. And so if you did, let's say, the cosine of theta would be x over r. So if cosine of theta is equal to x over r, then multiply the r over, and r cosine theta equals x. Similarly, it would equal y for sine of theta. But you don't have to know how to prove that to solve this. So if we want to find dy dx, that means we need to do whatever dy d theta is, and then divide out dx d theta. So if I can find those two, then I take the quotient. So the first thing I'd have to do then is write y in terms of theta. And so if y equals r sine of theta, and I know what my r is, which is this, I'm going to input that right there. So y is equal to quantity, 1 minus 2 sine theta times sine of theta. Or y is equal to, if I distribute that, that's sine of theta minus 2 sine squared of theta. Okay, now if I do the derivative of that, so then that means dy d theta is equal to the derivative of sine, which is cosine of theta. And then there's a kind of a chain rule here. The 2 comes down in front, so 2 times 2 is 4 sine to the first power of theta, but then the derivative of sine, which is cosine theta. So that much right there would represent dy d theta. So that's going to eventually become my numerator. Then to find dx d theta, to find my denominator, I'm going to do something similar. But first I need to write what x is. So x is equal to r cosine of theta, which means that x is equal to our radius, which was 1 minus 2 sine of theta, and then cosine of theta. So let's distribute that. So that means x is equal to cosine theta minus 2 sine theta and cosine theta. Well, here, again, derivative. So dx d theta is equal to, well, the derivative of cosine is negative sine of theta minus, and then I've got a product rule here. So I'm going to think about that as, well, the derivative of 2 sine, which is 2 cosine, leave cosine alone, plus, and then leave 2 sine alone, and the derivative of that cosine is negative sine, so times negative sine. So when I simplify that, I get negative sine of theta minus 2 cosine squared of theta, and then this negative distributes, there's a negative there, so that becomes plus 2 sine squared of theta. So now I have my dx d theta. So when I combine this to find the slope of the tangent line, right? And a lot of times you might just do it, at least on multiple choice. I would see that as at a particular point. Free response, I could easily see that as find it in general. So dy dx, remember we said was going to equal dy d theta over dx d theta. Right. So, and then we just put the 2 as a quotient. So, it's not going to be linear. Obviously, it's a trig function. So cosine theta minus 4 sine theta cosine theta, and then divide that by negative sine theta minus 2 cosine squared theta plus 2 sine squared theta. Now that's almost a Pythagorean identity, right? Except for they'd have to either be both positive or both negative. So then that would be our dy dx. So we would be able to figure out the slope of the tangent line at any given theta, which is pretty, which is nice. Now, there's a second part to this where it just says, well, how do you find vertical tangent lines, right? How do you find horizontal tangent lines? Well, if you look at how our derivative is defined, right, dy dx is defined as dy d theta over dx d theta. So if I'm trying to figure out when there's a horizontal tangent line, which is equivalent to having a slope of 0, then I'm going to simply look to figure out when is the numerator equal to 0, which is dy d theta. So you don't necessarily even have to find the entire dy dx if all you're looking for is to find a horizontal tangent line. You just set dy d theta equal to 0. And then from a similar standpoint, if you're just trying to find a vertical tangent line, that would be when your derivative is undefined. And since dx d theta is sitting in the denominator, we would set that equal to 0 and solve. Now, for our example, that's pretty challenging, right? Setting that equal to 0 would definitely involve using a calculator to find those points of intersection.